Energy. What is it? Okay, let's talk about it today. Well, energy, it's a very difficult question for physics. A standard textbook definition is something that enables an object to do work, but that's kind of not a very good definition um, for several reasons. Because well, what is work? Who knows? So, what is energy? Well, in general, we can think of energy as the ability to cause change. So, anything that we think of that has the capacity to influence and modify and adjust, something that has that capacity that can do that, then we'd say that thing has energy. Okay. So types of energy. Well, we've got a few of them, and there's even more than we could get into. We've got kinetic, we've got gravitational, we've got electrical, chemical. So let's talk real quick. These ones, let's get a pencil out. Um, when we see a chemical, I really wanted you to think about the energy stored in bonds. So we can actually store energy in chemical bonds, and you break that energy when you eat food. You break the bonds, you change the molecular structure of the carbohydrates and things, and you extract energy from that. Electricity, well, those are like electrons and other charged particles, and it's their location. It's actually kind of, at times, it can be very similar to gravitational energy, actually. Thermal energy, that's going to be motion of particles. Um, running out of a little space. Elastic energy. Well, that elastic energy is when we change the shape of an object. Now, certain objects have the ability to change shape, and then they want to return to that original shape. So, if you think about this, like think about like clay, and you can like change clay, but does it want to go back to its original shape? No. So it doesn't really have elastic properties. Things that do, the classic is rubber. Rubber is an elastic substance that when you change its shape, you will, in fact, it'll want to return to its original shape, and you can store energy in changing its shape. Nuclear, that is, in fact, hidden energy inside the nucleus of atoms. Nuclear energy is usually either breaking or splitting or combining nuclei to form either a larger nucleus or two smaller nuclei. So that's pretty interesting because when we do that, we're actually going to release energy. Okay, light. I talked about this in some of the classes. This is the classic electromagnetic energy. We'll call it electromagnetic radiation. And it sounds very scary, guys, but it's really important because it's how we see. And then magnetism. A magnetism, it may even seem like it's very connected to light, but it has its own unique things, and we'll talk maybe about this a little bit later. But magnetism has a type of energy. And last but not least, famously by Einstein, mass. Mass is energy. E equals mc squared. Energy equals mass times the speed of light squared. We can actually take mass and convert it to energy. Now, the thing about this, guys, is these are all different types of energy. They're all the same thing in different forms. They're the same thing in different forms. So we can, just like, um, we can have pennies and we have dollars. Well, those are the same thing in different forms. So you could have uh, gravitational potential energy and kinetic energy, and they're the same thing, but in a different form. And I don't want you guys to think about anything these things as being that different. Gravitational potential energy. One of the more popular ones for this class is the energy due to the position within a gravitational field. So when you're around a planet like Earth, due to your position in the gravitational field, you can actually have energy. We see this kid over here. If I were to raise this kid up using the powers of levitation, if I were to cause this person to go up in the air, let's cause this person to go up. Oh, let's see if we can draw a better arrow than that. Well, just get out the arrows. So let's cause this person to go up. If that person were to go up, we could increase their gravitational potential energy. In other words, it has the potential to cause change if released. So suddenly, let's say we could cause this person, I have like telekinesis, I can make things levitate, then suddenly I release it, they fall. Well, by making them levitate, by lifting them up, I can store energy in there. Now, one thing I want to talk, and I've got a little space here to talk about, is one of the other properties that's very important. Energy is a scalar, meaning it does not have direction. So no matter where this kid is, what he's doing, his velocity, his height, we cannot make that energy have a direction. It's like counting students. I can't have a negative amount of students. So that's the thing. It's a scalar. Very important. Okay, let's keep going. Calculation. Now the book. If you'll notice, is the book likes to do this. The Regents likes to do this. You don't have to, but the book gives you this formula: delta PE equals mg delta H, and that's good for determining the change in potential energy. But I am not the biggest fan of this formula. You can often just refer to this as PE. Trying to write with the mouse. Go back to the pen. PE equals mgh. They're both, guys, they're both correct. There's not really any difference between the two. But a lot of times the book likes to say delta PE equals mg delta H. You can use that, and I would say very cool if you did. Or you can just use PE equals mgh. Now the height must be measured from the same point on the surface of the Earth. That is where this can be a little bit confusing. And we'll go into that maybe hopefully a little bit this week. We could we could easily standardize this all. Like, we have to measure our height from the same height. Well, what height are you talking about? What point are you talking about, Mr. Shaw? You could measure height. Let's go here. Let's delete all this. Let's say we have a nice floor. Oh, that's a terrible floor, Mr. Shaw. Let's say we have a floor here. Let's say we're in the classroom. And let's say we're going to drop an object. Like this red ball right here. So that object's going to get dropped. Okay, well, where do we measure our height from? And you may say, well, of course, the floor, Mr. Shaw. But what if this object is so heavy it goes through the floor? There's a floor beneath our floor. So, hypothetically, if you wanted to measure this, the best place to measure all your heights from is the center of the Earth, because that's where every object would eventually fall to. But we usually pick one reference point, usually like the lowest surface possible. So when we drop things in the classroom, we'll pick the lowest surface that we deem possible. The lowest surface possible is where we start to measure our height from. And in this case, in the classroom, it's the floor. But if we were dropping extremely heavy objects, they could go through our floor, into the floor below our floor, and maybe even through that floor. So we could have some major issues. And where would we measure the height from? Well, the fail-safe is to always measure from the center of the Earth, but that can get a little ridiculous because that's a big number. So you usually stick with the surface of the planet, not the center of the planet, or just at one relative, the lowest possible surface. Like, we assume this ball is not going to go through our floor and it's not going to go to the next floor. So we'll just use the surface. Hope it's not too confusing. Now, we have h, which is our distance in the y direction. We have g. Now, notice this is a little odd nomenclature because you can just call meters per second squared meters per second per second. It's very cool. Notice that it's not negative. I have to keep it positive because it's scalar. And joules is going to be our unit for all energy. Now, kinetic energy is the energy of motion. When in motion, objects have energy. They have the ability to make changes. A dodgeball hitting in the face would change your day. It takes energy to get an object at rest moving, and once it's moving, it requires a loss of energy to bring it to rest. Calculations of energy. Ke equals 1/2 mv squared. We've talked about this a lot. And then we got mechanical energy. Now, we've been talking a lot about mechanical energy, and you maybe haven't quite realized it. Mechanical energy is a lot of times in this class referred to as total energy. ET equals PE plus KE. But this ET over here, you know, we went over in a list earlier a lot of the different types of energy. You notice it's missing chemical energy and all sorts of things over here. So usually in this class, when you see ET, you may think, oh, it's the total energy. But I'm not taking into account mass. Like, I'm not saying plus mc squared plus my chemical energy plus the thermal energy. No, we usually just say this right here, and this right here is our mechanical energy formula. Okay. I usually don't deviate too much from it. I usually just keep it as the main energy formula, but there are some places that will go a little bit more specific. Now work. and this is what we're talking about today, hopefully, or you've got some feeling about this. Work equals a change in energy. So work has its first formula here. Work equals delta E. So if you do work on an object, you change the energy of the object. Okay, so we're going to get into another formula in a minute about work, but this is where we'll stop.